the last lecture we had discussed about the oblique sock. If you recall, I also mentioned that oblique sock is like an can be treated as a normal sock with respect to the normal component of the inlet velocity, right. Why it is so, and how you can arrive at that conclusion is very important. You must relook at it. We have already derived, but I just want to mention that by invoking the conservation of momentum equation along the sock direction, right, we have shown that V1t, that is velocity along the sock in the station 1 is equal to velocity tangential velocity along the sock at station 2, that we have done. And then we derived several expressions for various properties ratio, P2 by P1, T2 by T1, and also the total pressure, temperature ratios, density ratios. If you look at all will be in terms of what? Inlet Mach number and also the outlet Mach number. Is it so? No, no. Finally, we derive into the inlet Mach numbers, and for that we also looked at a relationship between beta. Beta is which angle? If you look at your note, it is the angle of the sock, and theta is the angle of the wedge, right, and Mach number. And we have looked at that a beta theta Mach number diagram. Either you can use a diagram or you can use a expression what we had already derived, right. And now we will take up an example just to see how we can use and how we can compute the what you call properties for an oblique sock. And this is the example, that is a steady supersonic flow with Mach number M1 of 3, right, Mach number is 3, quite high, and pressure is P1 100 kilopascal, T1 is 298 Kelvin, enters into an air intake with a Wedge. Wedge means it is a 2-dimensional basically of included angle of 40. And we need to determine the sock angle, that is beta, exit Mach number M2, and exit static total temperature and exit static and total pressure. We need to determine all those things. So, for that we will look at the sock as it is, as we had seen this figure. Keep in mind that what I did in the last lecture that I took, if you look at, this is my solid surface, right, this is the solid surface, and the streamline is coming and adhering to the solid surface, it is making an angle theta, and in this case what will be this theta here? This theta will be 20 degree, not 40 degree, okay. And I have taken this control volume, and how I have chosen this control volume, did you get? Because these are the streamline, and keep in mind that we are taking care of the inviscid flow, or in other words we are considering the inviscid flow, right. There is no boundary layer, although it is a solid surface. This is your wedge, right, half wedge rather, okay. And then another what you call control, what you call the streamline I will take, and then we know that no mass will pass through this what you call streamline, two streamlines. So, therefore, I can put a this control surface along with the streamline, right. Similarly, there is a control surface over here, and then I will put this control surface parallel to the sock, that is very important. If I will not put parallel to the sock and rather perpendicular to the inlet velocity, then I will be landing in problem of handling equation. So, you please think about it little more and appreciate why I have chosen this control volume, the control surface A, which is I have shown here parallel to the sock, oblique sock. And then of course, like let us look at what we, what are the things are given in this example. M1 is 3 Mach number, P1 is given, T1 is given, theta is 20 degree. I have already told you this is the half wedge angle, right. And to find, if you look at what is to be found, if you look at, I need to find out beta, I need to find out M2, I need to find out P2, PT2 and T2 and TT2. So, these are the things to be found. Now, how will go about this? How? Because I know inlet Mach number, I know the inlet Mach number, then how I will do? That means I need to find out what is the sock angle, right. Should I not find out sock angle? Why should I find out sock angle? Because I want to know what is the normal Mach number to the, that means V1, no, sorry, that is what you call M1n I need to find out. For that, because if you look at what is this angle, right, beta, which angle it is? Beta is this angle, am I right? Right? Yes or no? So, therefore, I need to find out the beta, and what I will have to do? I will have to use beta theta m diagram, right, or I can use an expression, but generally it is easier and less time consuming to use a beta theta diagram, right. If I look at this diagram again and see that beta to be found out from this diagram, right. How I will do that? I know what? I know the inlet Mach number, and that line corresponding to what? This 3, this is the 3. So, this line is there. So, I know the theta angle is here, right, in this scale. So, I can find out what will be beta. Sometimes, like beta and theta are known in a problem, but you need to find out what is the Mach number, right. Okay. So, you can find out that, for example, if I just take this kind of a line, I will have to go a vertical line here, cross at this point, right, and if I take a horizontal line at this point, right, one has to be very carefully draw it, and you will get a line, and this point will be the your beta angle, and that happens to be maybe 37.8. We will see that from this we can find out to get that. And from that we are getting 37.5 degree, this is the angle, right. So, and by knowing this angle, right, by knowing this angle beta, I can find out what is M1n, that is this, there will be Mach number perpendicular to the oblique sock, right, M1n. It is, this is a vector velocity vector diagram, and Mach number you can have similar diagrams, right. So, then it turns out to be 1.826. Keep in mind that although it is easier to use beta theta m diagram, but it incurs certain error. We need to tolerate that error, and we will have to be very care not to make any silly mistake. So, Therefore, there will be little error in incorporating into our calculation. So, from this we have now like instead of 1.826, I will take 1.83 and then invoke a normal sock table or use a relationship for the normal sock, right. And if I know this inlet that is perpendicular to it is perpendicular to this one, right, to the circle to this thing, then what will be the downstream Mach number, which will be also perpendicular to the what sock, because so far this Mach number is concerned M1n and this is as if it is a normal sock. That means, we can treat a normal sock with respect to the normal component of the Mach number or the velocity, that you must keep in mind. So, what will be this downstream Mach number? That will be subsonic in nature, right, because always the Mach number downstream a normal sock will be subsonic, right, and more the upstream Mach number, the less will be the downstream Mach number. You must be knowing by this time, am I right? So, from the normal sock table we can get these values, if you look at the M2n is 0.6108 and sometimes you will have to interpolate, you will have to carry out a linear interpolation between 2 points, whatever is given in your table. Similarly, we can get T2 by T1, P2 by P1, these are all static temperature ratio, pressure ratio from the normal sock table, and total pressure ratio across this, which one? Oblique sock, but normal component we are considering, treating it as a normal sock, right. So, we will get these values. Hence, we can evaluate properties easily, right. What are the properties? Properties like your what will be the Mach number downstream of the oblique sock, what will be? Will it be subsonic or will it be supersonic or will it be sonic? It can be anything, am I right? What do you think it will be? It can be, depending on the things, it will be supersonic, or will it be all the time supersonic if the flow upstream Mach number is supersonic? So, let us look at how we can get very easily, because we know M2n, the M2n is 0.6108 and if you look at like this angle is what? This is beta minus theta, right, this angle. So, I can write down M2n, of course, see here I am showing these velocity vectors, but you can draw a Mach number vector similar to that, it is almost similar. Okay. So, but it is not the same. Okay. M2 will be M2n divided by sin beta minus theta. So, we know beta, because beta we have already found out 37.5. So, theta is known 20 degree. So, it becomes sin 17. So, we can get 2.03. So, if you look at this value is higher than the sonic value, m is equal to 1. So, therefore, it is flow is supersonic. And of course, other properties we can get, like for example, I want to look at what is the static pressure P2, P2 by P1, I know these values. So, I will just put P1, because P1 is given as 100 kilopascal. So, you will get 372.3 kilopascals. So, what you can see from here, this result, that means the static pressure downstream of the oblique sock will be greater than the inlet pressure. That means, upstream of the sock, that is P1, that means, in this case P2 is greater than P1. Similarly, we will see T2 is equal to T2 divided by T1 into T1, T1 I know. So, this is 462.T Kelvin, and if you look at T1 is 298 Kelvin. So, therefore, T2 is greater than T1, and we need to now find out what you call the total pressure. So, how we will do that? How we will do? We need to now invoke let us say PT2. So, what I will do? PT2 into PT PT2 by PT1 into PT1, I will get PT2, right. So, if you look at, I need to know PT2 is equal to PT2 divided by PT1 into P1 into P1, right. So, PT1 by P1 I can get with respect to this station corresponding to Mach number of 3. From the isentropic table, I can get PT1 by P, that is 36.37, right. Here in this case at the station 1, the flow is isentropic, right. Yes, is it acceptable? So, I can use that table and put that number here 36.37 and I know this ratio, and then what you call put these values and I will get 2942 kilopascal. And what will be? Will it be higher than the PT1 or it will be lower than PT? It will be lower than the PT1, that means PT2 is less than PT1, is not it, because point is coming. If you look at, if I take this out, then 36.7, that is basically 3673 kilopascal will be PT1 and PT2 is 0.8 of that, that is 2942 kilopascal. So, similarly, we can find out TT2, which is nothing but TT1, because we are considering to be adiabatic, and TT2 by TT1, actually there is little mistake here. So, TT1 by T, right, into T, that will be TT1 by T into 298.8314 Kelvin, right. What you see that TT2 is greater than TT1 or it is equal, it is actually equal because it is adiabatic, right. So, now we will see that some more aspects. Let us look at a wedge, right, which I have already shown here, which is having half wedge angle of 20 degree and the Mach numbers are 2. And if you look at, it is these streamlines downstream of the oblique shock is parallel to this surface, right. These are the surface of the wedge, all are parallel making 20 degree and also the shock angle is 53.3 degree. You know, this is a 2-dimensional body, that means perpendicular to the surface will be having some length which is quite large as compared to the this thing. This is a 2-dimensional, right. But now, in place of wedge, if I take a cone, right, what will happen if I will consider the same Mach number, right. Of course, there will be a formation of shock like Mach number 2 and some pressure, temperature, inlet, all those properties will be there. But will this streamline will go parallel to this? Yes or no? Please tell me. Certainly no. What will happen? This will be having 3-dimensional effect. That means, if the cone is there, right, there is a more chance for the shock to be adjusted, and because a mass can move into, because why this is occurring, mass being accumulated, therefore, the pressure is being increased and you are getting a shock, right. If you remember, I had told you how the shock being formed, because the supersonic flow will not be knowing that there is a disturbance itself, because the disturbance cannot propagate, you know, and reach to the fluid elements to be get adjusted upstream, right, because the speed of sound is less than the incoming fluid, right. So, therefore, but in this case there is a several what you call 3-dimensional effect. So, it becomes a curve kind of things, right. If you look at these streamlines become curves and it will be changing as it go away from that, and keep in mind that as a result the shock angle is being reduced, that is 37 degree in this case, whereas the in case of a wedge this is 53.3 degree, and the strength of the shock will be decreasing in case of a cone, right. And if you look at it is not making angle 20 degree right, which is supposed to be, it is changing, these slopes are changing. In this case it is 8 degree, but as it goes it may be increasing if you look at. So, this is a very important aspect, that means for the same Mach number, right, same inlet conditions, the cone will be producing weaker shock, right. That is why we use that in the air intake. Of course, it will be having several other problems, but it is preferred to use a cone over the wedge. But in our what you call calculation, what we will be doing, we will be using wedge, because the analysis of the cone, the shock formation over a cone, considering a cone, will be quite complex, and it is beyond the scope of the present lecture, right, present course. However, some of you are interested to look at it, you can look at it advanced books on gas dynamics. And whenever if you look at most of the problem, we will be looking at wedge, and it is a simpler to handle, and also it is being used from in the practical air intake for several other consideration. Now, let us discuss it little further, that if you look at, there is a wedge over here, and this is the wedge making an angle theta, and the streamline is adhering to this wedge. This is the 2D wedge, okay, keep in mind. And then flow will be in the 2D, and all we have seen that M2 is less than M1, rho 2 is greater than rho 1, P2 is greater than P1, and T2 is greater than T1, all those things we have seen. But in case of this wedge, now we will say that it is going in the opposite direction, that is there is a solid body which is turning convex with an angle of theta shown here, right. What will happen? Flow will be, because it is a 2D again, the flow will be parallel to this solid surface, but however, it is going through a several expansion fans. That means, it will be expanded to adjust into that, right. If you look at, it will be just opposite that of the an oblique shock, because there it will be compressing, here it is expanding. So, it will be taking a smooth turn over here and do that expansion. How to handle those expansions and other things, I will not be covering, but you may read little bit, because we may need to understand this expansion process, and which can be invoked while discussing about over expansion nozzle, under expansion nozzle kind of thing. So, I would urge you people to read little bit more about expansion processes, and particularly Prandtl-Meyer relationships and other things, but those relationships we will not be using, but we will be talking about more qualitatively, considering what I have covered in the class, right. Now, let us move into another topic, that is, till now we have looked at the properties being changed in case of formation of shocks, whether it is a normal shock or a oblique shock. But the properties can also be changed if there is a heat addition, for example, in case of a combustor, right, in a gas turbine combustor, rocket combustors, where we will be adding a large amount of heat for producing a thrust. Okay. In that case, what happens to the properties? Of course, considering a very simplified version of flow, like one dimensional flow, right, like what I have shown here. I have shown here one dimension, these are the properties P1, rho 1, V1, T1, and there is a heat addition over here, and what happens to the properties of P2, rho 2, V2, T2. And this flow we will be looking at now, and learn how to handle this kind of situation, because it is having practical implications. If the flow is subsonic, what happens? If the flow is supersonic, like your supersonic vehicle like scramjets and other vehicles, ramjets, then we need to understand that what is really happening, right. So, and that we will be looking at, one dimensional flow with heat addition, and that is being known as a Rayleigh flow as well. So, we will do standard assumption, which we have already seen, that is one dimensional steady flow, we are considering steady flow, inviscid flow, that means no effect of what you call boundary layer or the friction, no gravitational force, ideal gas, no work interaction and no work done by the shear force. There is no friction on the wall or any other place, right, and constant thermodynamic properties as usual we take for simplicity, but however in reality it will not be, because there is a heat addition, temperature will be changing, Cp is a function of temperature, right. So, also it is as its combustion is taking place, the what you call various molecules and other things will be getting changed, generated and kind of things. So, we can't really talk about it, but however for simplicity we are considering. So, let us look at the mass conservation equation for this, and I have taken this as a control volume. So, if you invoke this mass conservation, you will get rho 1 V 1 is equal to rho 2 V 2, right, which is very simple, which we have already done. So, similarly for momentum equation, we will get rho 1 V 1 square plus V 1 P 1 is equal to rho 2 V 2 square plus P 2, right. Whatever the assumption we have made, we can consider and get this expression. And similarly, energy equation is very obvious except to you, except that there is a heat addition. That means, this is a total enthalpy. If you look at this is the total in enthalpy plus heat addition and total enthalpy at the downstream, right. That means, whatever the enthalpy is coming in plus whatever the heat being added is equal to the total enthalpy at the downstream. That is a one dimensional flow, which we have already seen, right. So, ideal gas law as usual, P is equal to rho R T, and what we will do now, that we will just take this momentum equation, rewrite P 2 minus P 1 is equal to rho 1 V 1 square minus rho 2 V 2 square, right. And what we will do, if you look at, like, we need to express this rho V in terms of gamma by using the definition of m, that is the Mach number, and we know that V square is equal to m square gamma R T, right. And if I say that there is a rho over here, that means rho V square is equal to m square. If you can write down rho V square is equal to m square gamma rho R T, and this is nothing but your P, right, from ideal gas equation. So, I can write down rho V square is equal to gamma m square P in these terms for the station 1, similarly for the station 2 gamma P 2 m 2 square, right. And if I will simplify it further, I can get it is P 2 by P 1 is equal to 1 plus gamma m 1 square divided by 1 plus gamma m 2 square. Could you recognize this equation? It is similar to what? Similar to your normal shock relationship, the pressure ratio across a normal shock, am I right? Can you look at your notes? And by using the equation 4, we can derive an expression T 2 by T 1, because I can look at this for ideal gas law, and then I can rewrite that as T 2 by T 1 is equal to P 2 by P 1 into rho 1 by rho 2. In place of rho 1 by rho 2, I can invoke write down from this conservation mass conservation equation as P 2 by P 1 into V 2 by V 1. V 2 by V 2 by V 1 is basically substituted for rho 1 by rho 2, and we can use this definition of Mach number and then write down, that is V 2 is nothing but m 2 A 2, and similarly V 1 is m 1 A 1, and in place of A 2 I can write down gamma R T 2, and if I simplify I will arrive at P 2 by P 1 m 2 by m 1 root over T 2 by T 1, right. And if you look at the left hand side here, and what if I cancel it out, you will get a relationship, that is root over T 2 by T 1 is nothing but P 2 by P 1 into m 2 by m 1, right. So, I can write down this as root over T 2 by T 1 is equal to P 2 by P 1 m 2 by m 1. In place of P 2 by P 1, I can use this expression, right over here, and square this equation, I will get T2 by T1 is equal to 1 plus gamma m1 square divided by 1 plus gamma m2 square, m2 by m1 square I can get, right. I am using equation 5 here and just substitute in this place and you will get this expression, right. That is the temperature, static temperature ratio. Keep in mind that this both the pressure ratio and the temperature ratio is a function of what? Is a function of Mach number and gamma, right. And by using equation 4, that is again the ideal gas law, and we can get this expression for density ratio, which turns out to be pressure ratio and temperature ratio. We just substitute over here, you can simplify, right, and get this expression, which is very expression kind of thing. Now, all these expressions are function of m1 and m2, right, and we will see also the temperature, total temperature ratio, pressure ratio, but we need to find out how we can solve unless we know the m2, right. If I know the m2, then this expression will be very easy to find out various properties ratio across a control volume in which heat being added, right. So, similarly, total pressure ratio we can find out, that is PT2 by PT1 is equal to PT2 by P2 into P2 by P1 into P1 by PT1. If you look at expression, this is nothing but that, this portion, right, and PT2 by P2 is nothing but your what you call the 1 plus gamma minus 1 by 1 plus gamma minus 1 divided by 2 m2 square, and here that will be PT1 by P1 will be nothing but 1 minus gamma minus 1 divided by 2 into m1 square.
So, all these relations are derived from adiabatic flow like PT2 by PT1.
Yeah, but yes, you are right, but if I consider only station 2, there all my heat being added is over. I mean, I am not adding anything at that point. So, therefore, I can consider this as an isentropic flow. I think I need to look at the what you call, maybe I will draw over here, right. This is my control volume CV, this is my station 1 and this is my station 2, the heat being added over here. So, so far the station 1 is concerned, I am not adding any heat here at this point, am I right? So, I can consider this as a PT1 divided by P1, isentropic relation for PT1 divided by P1. Similarly, at the station 2, right, at this point, I can consider very easily the same thing, because all heat being added by the time fluid reaches the station 2. So, I can happily use the isentropic relationship. Is that clear to you? Okay. I can do as this is a properties, like I can do it because I am not doing anything, I have already added, right. That is the way we can do that. So, similarly, total temperature ratio can be derived, TT2 divided by T1 is equal to T2 into T2 by T1 into T1 by T2, and this is a similar expression. It looks to be quite complex, but it is taken from earlier relationship, and these are isentropic relation. If you look at these are the heat addition relationship between the inlet and outlet of the control volume where it is being added, and this relation is for isentropic flow, right, at the station 1 and station 2. So, now we know the Q. So, I can find out what will be TT2, because I know TT1. If I know this TT1, I know the Q, that is heat being added, I must be knowing, then I can find out what is the TT2. If I know this TT2, because this is known as, this is known, right, and this is known. That means, we can find out T T 2. By knowing this T T 2, I know this ratio, this will be known. Then how I will find out, because this is known, M 1 for inlet condition should be known, right, but can I find out M 2? You know, this is a nonlinear equation, you need to go by trial and error or some other numerical techniques to get that, which is the, but right. That means, if we know this M 2 for any flow conditions, we can very easily do it, but however, it is quite difficult to get a closed form solution directly, right. And as I told, one can do by trial and error, and we can have a what you call a table and then use those tables, right. But to solve I mean like these things, then what I will do? What I will do? I will use all these problems, I will be taking using a characteristics Mach number, that is M star. That means, all the inlet conditions, like for example, here one inlet condition, I will take to the sonic condition. Similarly, the station 2 I will take to the sonic condition, that is M is equal to 1, and then I can come back and then look at it. For this, I will be taking an example to illustrate this point, but let us look at, we need to find properties with respect to the sonic condition. I will take the equation 6, right. Okay. If I will consider that M 2 became 1, right, because this became 1 sonic condition, right, for a particular M, then what will be? This also will be 1, right. Similarly, instead of M 1, I can write down this is M square, and similarly this I can write down as M square, because there is no M 1 M 2, it is the only the Mach number to generalize it, and M 2 is anyway it is going to the sonic condition, right. So, I can write down an expression. If you look at what I am getting here 1 gamma, right, M 1 square, right, okay. And what I am getting here? I am getting here 1 plus gamma M square, right. So, if I take this M square out, I will get T by T star 1 plus gamma divided by 1 plus gamma M square, right. So, similarly, I can get P by P star is equal to 1 plus gamma divided by 1 plus gamma M square, and similarly, what you call rho by rho star I can get from those expression, keeping that M 2 is going to the M star or the 1, M is equal to 1, M 2 becomes, and M is generally one Mach number, any Mach number it can be subsonic, it can be supersonic kind of thing. So, these are the relation we can get for the sonic condition P T by P T stars, right, and T by T T stars, all these expression we can get from the expression like equation 9, 8, 6, 7, all those 8 we can use and get this expression, just putting M 2 is equal to 1, right, M 1 is equal to M. So, we can get this expression and it can be tabulated, and a table known as Rayleigh flow table or Rayleigh table, right, we can use that. Now, let us consider an example, right, that is the fuel air mixture enters the gas turbine combustor with a velocity of 78 meter per second at static pressure of 50 kilopascal, right. If you look at velocity is quite low, this is 78 meter per second, and pressure is 50 kPa, and temperature is 400 K, and during combustion heat for unit mass, that is 15 kilojoule per kg is being being released in the combustors, and assuming the combustion chamber to be constant area, this is an assumption which is not the case most of the combustors, but we do use for the simplicity, and with negligible friction, there is no friction, but in real situation friction will be there. We will be considering how to handle friction in the next lecture, and we need to determine the properties such as T 2, P 2, M 2 at this downstream, and keep in mind that this is not air, therefore, we will be taking gamma 1.33, of course, gamma 1.2 you can also take depending upon what kind of fuel and air you are using, and Cp is need not to be 1.005 kilojoule per kg Kelvin, we need to take proper Cp, right. Although it is can be, and we can also use different Cp at station 1, station 2, we can do that. But in this problem we will be using the will not be using. So, given that if you look at V1 is given, T1 is given 400 Kelvin, V1 is given 78 Kelvin, P1 is given, Q is given, and gamma, all these properties are given, but we need to find out the properties like at the downstream like P2, V2, M2, T2 kind of things. So, what we will do? We will have to first find out the Mach number, that is V1 divided by A1, and this is gamma RT, this is gamma, this is R, and this is T. Again the R will be different, because if you are not using A, you are using some different, you should take care, but unfortunately I have taken the air value here, okay, but actual value will be little different. So, then 78 divided by that, it happens to be 0.2, which is a very subsonic case, right, because it is, you can consider the flow to be incompressible almost, but in some situations it will be little higher subsonic, right. We have taken this example, and from the isentropic relationship we can determine what will be T1, because I know T1, I know the Mach number. So, I can find out what it would be, right, and in this case it will not be very different, and that we can determine by T1 is equal to T1 1 plus gamma minus divided by 2 m1 square. If you substitute these values, you will get, that means in this case T1 is approximately equal to T1, there is not much difference. What is the difference? 2.6 Kelvin, it is not really much, right. But however, for completeness sake we are doing it. And similarly, PT1 you can get, this is a very low values 51.3 and the P1 is 50. So, it is not really very much difference. So, let us now estimate Tt2 at the exist, that means at the station 2. How we will do? It is a very simple one, because we know Tt1, right. Tt2 is equal to Tt1 plus Q by Cp. Cp is given here, right, and Q is given, this is given, this is given, this is given. You will just substitute those values, you will get 1573.6 Kelvin, right. Now, of course, inlet is 400, that means you have added enough heat to have 1573 Kelvin. If you look at its typical temperature, right, one n can get, but nowadays of course higher temperature is being used at the exit of combustor for expansion in the nozzle, particularly gas turbine. So, let us what you call, now we have already seen that like we know this is known, this is known, we need to find out, and this is known, M1 is known. So, we need to find out M2. What we will do? It is quite difficult to do by trial and error. As I told you, we need to use this characteristics condition for a inlet. For that, let us consider that this is our problem with having a station, M1 is given, P1 is given, T1 is given, and you are going to M2.46, that we have already determined, right. Is it we have determined this? Certainly no, we have not determined, we need to find out. Similarly, we need to find out P2 and we need to temperature T2, right. We need to determine this portion, right, at the station 2. How I will go about it? Because using this expression, right, it is quite difficult to get a solution directly when a closed form solution, right. We will have to do trial and error or some numerical methods or something like that. So, what we will do that now, I will assume that as if my heating is being done from the station this condition, right, such that it is going to the sonic condition, that is m is equal to 1, is a virtual, or what you call you are just doing, it is not actually happening, you are extrapolating it to the sonic conditions such that this is the Q1 star. Okay. This Q1 star is not same as the Q, keep in mind that. Okay. Now, if I know this condition, I know these properties I can find out. Similarly, I will look at another condition which is M2, right, condition, and this condition is same as that of that, then I will come back and get these conditions. That means, I am looking at from here station 1 to the star I am going, from here to I am coming to the star, then coming back to here, right. It is just you are trying to do in a little easier way. So, if you look at q is equal to q1 star minus q2 star. So, we will see now how we are doing, how we can solve this problem. So, for M1.2 by using equation I have already told shown you 10 to 14 we can determine properties ratio with respect to Sony condition, that is M is equal to 1, right. We have already derived those expressions like equation 10 to 14, we can use those things or we can use a table, right. I have taken from here, I am using directly those expressions, and when you use directly you will not incur any error, right. So, if I will put these values, that is 0.2, if I look at here you get is T 1 by T star is 0.196, because I know gamma is 1.33 and M Mach number I know, I will get this. Similarly, other properties I will be getting P 1 by P star, you will get 2.21 and P T 1 by P T star, you will substitute these values, you will get 1.23, right. And similarly, T T 1 by T, you will substitute these values and get 0.17. And we can determine T 2 by that. What we have done? We have looked at what you call this thing from this is 1 and this is star condition, right, Q1 star. This is the 1 condition, that is Mach number is equal to 0.2, but in actual situation it will be something different, right. We have taken to a fictitious of the star conditions, right, that we have done. Now, we will have to go to the inlet, because T 2 is known and I will have to find out T 2 by T T star. What I will do for that, like T T star by T T star is nothing but T T 2 divided by T T 1 into T T 1 by T T star, because this, right, okay. And if you look at this I know, right, that is 0.17, that is T T 1 by T star. Of course, there will be a star here, right, 0.17, and this I know because T T 2 is known, this is known, this is given, rather T T 2 I can find out, we have already find out. So, I will get this one. If I know these values from Rayleigh flow table, right, which the table will be there, or you can use this expression, similar expressions, you can find out M 2 is 0.48. What you are observing? That the inlet Mach number was 0.2, but when you add heat, right, when heat is being added, it has been increased Mach number, and T 2 by T star we can get these values, P 2 by P star and P T 2 by P star, all from the table or from the equation you can use, because once I know M 2, it is very easy to get those things, right, and then we can determine T 2 and P 2, because I have already got everything with respect to the star conditions, right, or the sonic condition. So, T 2 is equal to T 2 by T star into T star by T 1 into T, this already you got the values, right. This is equal to 0.7587 and T 1 by T star already we have got 0.196, right, that is 1 over of that, and you can get this is 400, you can get this 1785.2. So, similarly, P 2 you can get this value, substitute, because this is known already from here, right, this you can get from here, and P 1 by P star we have already determined, that is 1 over 2.1, 21 and 50, you see that the P2 is P2 in this case, P2 is less than P1, right, because P1 is your 50 and this is 41.0, although it is very less because inlet Mach number is quite small. Similarly, T2 of course always will be greater than T1 because you are adding heat. Similarly, total pressure if you look at it is 50.91 and this is PT2 is less than PT1 because this is your PT1. And similarly, the density if you look at, you can estimate like 0.08 kg per meter cube. So, I will stop over here, we will see in the next class like what are the properties, how it is changing and what will be implication of those things in the next class. Okay. We will stop over.